We're going to study the common emitter amplifier, also known as the Class A amplifier. It is a BJT in a circuit designed specifically for a particular gain. We're going to examine the DC circuit, and we're also going to understand the AC operation. We have to look at this circuit in three stages: the input stage, which would consist of this loop here, Vin and R2, and then the amplifier stage, which is everything in the center here. And then we have the output stage, which is connected to the collector. And eventually we're going to look at the effect of adding a load at that output. So let's start from the beginning. Here we have our circuit. You can see the amplifier in the center. And we have a supply voltage of about 20 volts. We see our RC is 1 kilo ohm and the emitter resistor as well. We have a voltage divider here where we have a potentiometer set to about 34% of its full value. So 34% of 25 kilo ohms is what we have up here. And that is going to share voltage with the 5 kilo ohm below. So we'll only look at the DC components right now. We're going to ignore the capacitors, and we're going to ignore the input stage here, as well as a load that I have waiting in the wings. We're going to set the current through the BJT using this voltage divider. The voltage at the 5 kilo ohm resistor is passed on to the base emitter and RE. So I can actually set the value of the collector current by setting the value of RE here. KVL would demand that the voltage all sum to 0. You know that when the transistor is conducting, when it's on, you're going to have a 0.7 drop, about 0.6, 0.7 volts around there across the base and emitter. The rest of the voltage goes across RE, which essentially sets my collector current. Now we have to understand the importance of RE. RE provides us negative feedback. When we turn on our AC circuit, RE will not factor in anymore. So let's be clear that right now, this effect that we're about to talk about only occurs in the DC mode, in the DC operating mode. So assuming there is no input, so we're in the quiet mode, we also call it the quiescent mode, there shouldn't be any change to our operating point once we fix the voltage divider. But in fact, transistors are very sensitive, and the beta factor, or HFE coefficient, that amplifies the base current can change with temperature. When it does, it's going to increase the voltage across RE. So that voltage is part of this loop here. We see that the 5 kilo ohm voltage is going to be fixed by the VCC and the voltage divider. So that's not changing. But RE will rise if the current through the collector rises. That's going to squeeze the voltage across the base and emitter. KVL demands it. That's going to reduce the base current, the current that's feeding the transistor. That's going to reduce the collector current then. This is a stabilizing factor. It's negative feedback. Likewise, if the current drops below a certain, well, if it drops at all, the emitter resistor, that voltage will also contract. It will shrink, which means that there'll be more voltage across the base to emitter. That increases IB and the collector current, stabilizing it. So this is our preferred configuration. It gives us the greatest stability in the DC mode. In the next video, we'll look at the AC operation.